Okay, today we're talking about parent functions and transformations. We are going to be discussing each of these types of functions, and these should already be in what you call your library of functions. These functions you should be familiar with. We're going to talk about moving them around, the different changes that we can do to the graph by just looking at the equation. And I use a method of key points and knowing the shape. So each of these, you need to know the shape of the parent function and the key points, and that will make the rest of the lesson easy. Okay, so we're going to look at the 8 most commonly used parent functions. The first one we have is our constant function. Of course, that means that nothing changes, and that is f of x equal to c being a constant. Okay, in this particular picture, it would be y equals 3.5 or f of x equal 3.5. So you're only seeing one variable in your equation. Okay, the identity function is basically any other line. You might be a little more familiar with y equals mx plus b. Okay, but they're calling it the identity function because it is in essence y equals x. If you our b comes from when we learn how to shift the graph up and down. Okay, and m of course is representing your slope of rise over run. But more importantly, these two functions, there are no exponents on those functions. So then we go into our quadratic function, which has the u shape, and the key points of our quadratic function are we take 1, 2, and 3, and if you square each of those numbers, you get 1, 4, and 9. And the vertex is at 0, 0, but it gets moved around, so I generally don't refer to it as a key point. We go find the vertex, and then we use our key points or a rate of change actually to do that one. Then we have our cubic function. Okay, our exponent is 3. The key points that we have on this graph are negative 1, 0, and 1. Negative 1 cubed. Okay, that's right here on my graph. 0 is again that center point that'll be moved around, and then 1, 1. More importantly, if I have 2 and I put it in there and I cube it, I'm going to get 8. So I do know how to go to the next spot. If I had to go over 2, I would go up 8 on that graph. All right, then we have the square root function. All right, and it is, of course, somewhat the inverse of our quadratic function. So we can take those key points that we had up there and just flip them. So we have 1, 4, 9, and now we have 1, 2, and 3. So you're starting at that 0, 0 again, just like we had up there, and that'll shift with our transformations. But if we go over 1, we go up 1. If we go over 4, we go up 2. If we go over 9, then we're going to go up 3 to graph it. And then you have your reciprocal function. The key points on this graph. Key points also referring to as somewhat of a rate of change. Okay, we have negative 1 right here. We have, I mean, at 0, 0 again is that center point. It's actually not a point on our graph, so we refer to it as the center. It's where our asymptotes intersect. We do have the point 1, 1. Okay, so in each of these cases, we're going from the center over 1, up 1, or to the left 1, down 1. Now, keep in mind, it's the reciprocal, so if I put in 2, I would be at 1/2. So if I go over 2, I'm at 1/2, or if I went 1/2, I would go up 2. Okay, and also remember, because we will be shifting these around, that we have asymptotes at x equal to 0 and y equal to 0. So these are the key features of each of these graphs that you should remember. All right, two more. We have the absolute value function and the greatest integer function. In the absolute value function, I think most of y'all will remember that it is your V shape as you see on your graph. But what's going to be the key to remembering it is, again, once you find that vertex point, that your slope is plus or minus 1 until we apply changes to it. So when my vertex was at 0, 0, I went up 1, over 1, up 1, over 1 in both directions. Okay? And then we have our step function, also called step function. It is the greatest integer function, and the most important thing you want to remember are these words. The greatest integer function, looking like this, is defined as the greatest integer less than or equal to x. So pick a number that you need to know, and they give you lots of examples here. The greatest integer less than or equal to -4 is -5. Excuse me, -4. Think about it on a number line, okay? 0, -1, -2. The negatives tend to trip people up, okay? So if I'm on a number line and I choose the number -4, the greatest integer less than or equal to -4 is -4. But if I go to -1.5, what is the greatest integer less than or equal to it? So you're always going to the left. So it is at -2. So if you see we had, hopefully they'll stay there. 1, 2, 3, 4. -4 is right there. But then when we went to -1.5, we went down to -2. Because any number that's not an integer, you've got to go to that integer that comes right before it. Okay? 1/3, what's the greatest integer less than or equal to 1/3? It, of course, is 0. So pick a bar and remember it if you want to do the 0. It starts at 0 all the way over till you get to 1, and then there's a hole, and then it jumps up, and that repeats. Okay, and we write that when we don't have our fancy computer with just a single bar, brackets like that. If you want to double them, you can. Okay, let's talk about the transformations. First off, what do you need to know how to do? A translation, okay, a vertical or horizontal translation is when you are adding or subtracting a number from your function. Okay, and when we look at the functions, I am going to ask every time when I look at it, is it affecting the inside or the outside? Because if you'll notice, every time if it is on the outside of the function, k is on the outside here. It's not in those parentheses. H is on the inside over here. Okay? So if it's on the outside, it affects the y value, and we do the same thing. This is on the outside. It says plus k. I'm going to add k to the graph. This is on the outside. It says minus k. I'm going to subtract k from every y value. Okay? If it's on the inside, it affects the x, and you do the opposite. So this h is inside. It looks like subtraction, so we do the opposite. I'm really going to add, which is why we went to the right instead of the left. Okay, let's look at some examples of how we're going to use this. So we have use the graph of the function f of x equals x cubed to graph each function. So first and foremost, I'm going to figure out that parent, remind myself of that parent function. So I'm going to come down here and say that I know my key points are -1, -1, 0, 0, 1, 1. And I know that my graph, I'll put it here, my graph looks like that crazy little S thing. Okay? That is the general shape of my parent function. So I look at this particular one and I say, is that on the inside or the outside? It's on the outside. So it affects the y value, and I do the same thing. So I'm going to take my key points, and my x values will stay the same, -1, 0, and 1. But I'm going to subtract 5 from every y value. So -1 minus 5, 0 minus 5, and 1 minus 5. And then I plot those points. Keep in mind, this is like that center point of your graph. We've moved it from 0, 0 to 0, 1, 2, 3, 4, 0, -5. And then I had -1, -6, and 1, negative 4. And then we do our best to make it that shape. Okay, I'm going to let you get away with that. If we went over 2, from that center point, if I went over 2, I would go up 8. So don't cross this line unless you plot that point. Over 2, 1, 2, 3, 4, 5, 7, 8, it would be up there. So you would cross at that point. All right, let's look at 2b. I'm going to take this, and is that 3 on the inside or is it on the outside? It's in my parentheses, so I'm inside my function, which means it's going to affect the x, and I'm going to do the opposite. Okay, so my key points, this time my y values stay the same, and my x's, I do the opposite. So instead of subtracting 3, I'm going to add 3. So negative 1 plus 3, 0 plus 3, and 1 plus 3. So we go plot those points, and I have, and this is kind of that center point, 2, negative 1, 3, 0, and 4, 1. And hopefully that's enough for you to see that your graph is going to have that shape. And again, don't cross that line, because when we go over 2, I got to go up 8, which is off the graph up here. Okay? And now the last one, we actually have 2 of them. Okay? Is this one inside or outside? Hopefully you answered that was inside, so it affects the x, and we do the opposite. This is on the outside. It affects the y. I do the same thing. So, on my key points, these are my key points, remember. What do I do to the x values? I do the opposite. So I'm going to subtract 2 from every x value. Negative 1 minus 2, 0 minus 2, and 1 minus 2. What do I do to every y value? I'm going to do the same thing, so I'm going to add 4. Negative 1 plus 4, 0 plus 4, and 1 plus 4. So those are my points, and this is that center point of my 0, 0. So I go negative 2, 1, 2, 3, 4. And then I'm going negative 3 is at 3, and negative 1 is at 5. And I know the shape. So keep in mind, if you don't know the shape, then you would consider to draw, or might think about making this a line. That's why it's important to not only know the key points, but also know the shape. Okay. Okay, so the next change we got to talk about is reflection. And we've talked about this a lot before. Okay. When you have something reflected in the x-axis, okay, that means that your y value changes, okay? So every y becomes the opposite of what you had. If you reflect it in the y-axis, then every x becomes the opposite. So keep that in mind, and let's see how we're going to use that. We want to describe the graphs of 1 over x and g of x and how they are related. Okay, so let's have a reference point, and our reference point of 1 over x, I'm just sketching it. It looks something like this. Okay, I have an asymptote at x equal to 0, y equal to 0, pretty bad graph, and my key points are negative 1, negative 1, 0, 0, that's my center, doesn't touch that point, and 1, 1. Okay, so when you look at a graph, first off, do I have this first and third quadrant occupied? And I don't. Okay, you might want to consider putting some asymptotes in there or seeing where they are. So it looks like we have an asymptote right here, and we still have this asymptote right here. So what that has done to my graph, this line is y equals negative 2, and this is x equals 0. So that should be enough to tell you that it's been shifted down 2 units. Okay. It's shifted down 2 units, and then as we just pointed out that it's got the opposite. So when it's been flipped, actually, let me change color on you. If I, this would be the graph, of course, of y equals negative 1 over x. So that's what we have to start off with. We have y equals negative 1 over x, because I just flipped it around the y-axis, and it has been shifted down 2 units. That affects my y. When I do the y, it's outside, it's not with the x, and I do the same thing. So that gives me y equals negative 1 over x minus 2. They want me to write it as g of x, so we'll write g of x equals negative 1 over x minus 2. Okay, let's look at the next one. Let's go find those asymptotes to draw them. We have, looks like we have one here, and we have one here. So we label each of those. This is y equals 0, and this is x equals 1, 2, 3, negative 4. Okay. Again, my graph has been flipped. So I have y equals negative 1 over, my y value didn't change, so I'm not having anything on the outside, but my x value did, and I do the opposite. So if it says negative 4, I'm going to write plus 4. And of course we got to put that as g of x. So g of x equals, which I could have done in the beginning, negative 1 over x plus 4. And that is, I didn't, we talked about it. To describe the graphs you would put in words. Let's go do that. Okay, because I did realize it's asking us to describe. So what you would say here is you would need to say the flipping part first. Flipped, or we should use a better word. Let's use reflected. Reflected over the y-axis. You got to say that part first. And shifted down 2 units. That's how you would describe it. Okay, let's go describe this one. Over here, it is again reflected over the y-axis. And this time it has been shifted to the left 4 units. Okay, the last type of change, don't let this word scare you, okay? You might have talked about it before, you might not have. These are dilations, okay? You've talked about them earlier, or probably in a previous class. Compressions or stretching, expanding, stretching, okay? Same thing we've been talking about, but this time, instead of adding or subtracting to your graph, your function, you're actually multiplying or dividing a number, okay? But the same rule applies, and that is if it's outside, it affects the y. We do the same thing. If it's inside, it affects the x, and I do the opposite. So every time I look at an equation and I see some numbers added, I'm going to look to see the numbers, are they inside? I'm going to ask those questions of myself. Is that number inside or outside? And then remind myself what it's going to affect. So let's go look at our equations that we have. Examples to do. Identify the parent function of f of x and g of x. Describe how the graphs are related, and then graph them on the same axes. Okay? So hopefully you can see in this first example that our parent function is f of x equals the greatest integer less than or equal to x. Okay? And remembering that our key points are that we start at 0, 0, we go to the right, and we have a hole. So we graph this, and I'm just going to do a couple in the interest of time. You got the idea. You do need to do this when you do it. You got to go on both sides of 0. Um, and ideally, you would fill up the whole graph. So what I could do, all right, so we will stop it there. You got the idea? All right, so that's my parent function. What has happened here when you look at this is that the graph has been shifted. Okay, is this inside or outside? It's outside. I'm adding or subtracting, which means it's a shifting up or down. Outside affects the y, and it's going to go, I do the same thing. So I know that my graph has been shifted down 4 units. Okay, that's my description. So wherever you start, it doesn't really matter. Take a point, go down 1, 2, 3, 4. 4 units, and you draw it. And from there, it's the same pattern. So you would continue to fill up your graph from there. Okay, look at our next example. G of x equals 5 over x plus 3. So hopefully you can see that our parent function f of x is 1 over x. Okay, and my key points on that graph, negative 1, 0, 1, negative 1, 0, 1, and 0, 0 is where my um, asymptotes intersect. So I have one asymptote at y equals 0, one at x equal to 0, and then to plot it, I've got my 1 and negative 1. And I'm going to do my best to approach each of those axes asymptotically. Big fancy word for you. Okay, so now let's dissect the graph, or excuse me, dissect the equation. All right, it doesn't matter which one you look at first, but we're going to talk about which one to graph in the order. Okay, this 3, is it inside or outside? Hopefully you answered outside. It affects the y. I do the same thing. So if I'm adding or subtracting, that does what to my graph? That shifts it up 3 units. Okay. Then I have my 5, which from my parent function, what did I do? That is again outside because it'd have to be with the x for it to be inside. So it's outside again. Uh, does the y, does the same thing. And what does it do? I'm multiplying this time. So I'm multiplying, that's when we say it's a vertical, it's called a vertical because it affects the y, stretch of 5. Okay, now keep in mind, that's my description. This one is multiplying and this one is adding. Which one do I do first? Since I'm doing them to the same variable. Remember, both my x values are affected. Excuse me, both my y values are affected. My x's are staying the same, okay? You follow it just like your order of operations. So we always do multiplication before we do addition and subtraction. So that means my y value, I'm going to multiply it by 5 and then add 3. So negative 1 times 5 is negative 5 plus 3 is negative 2. 0 times 5 is 0 plus 3 is 3. And 1 times 5 is 5 plus 3 is 8. Okay? Now apply the same thing to your asymptotes. Okay? My x asymptote, or my x value asymptote does not change. I still have x equals 0. My y value asymptote, I'm going to multiply it by 5 and add 3. So now my asymptote is at, that's really bad. Let me go use my little helper because he can do better. Is at y equals 3. Y equals 3. And you'll see how that matches up with our points. So I have, I'll go ahead and put this one on there too so you can see it's a little bit harder to read. Okay, so those are the asymptotes of our new function. Negative 1, negative 2. Negative 1, negative 2 is right here. 1, 8 over 1 up 8 is right here. That's from the origin. That's the point, okay? But the nice thing about this is that's your symmetry to your graph. So if I go over 1, 2, 3, 4, 5, then I'm going to go over 1, 2, 3, 4, lost count, 1, 2, 3, 4, 5, up 1. That's your other point that allows you to draw it. Don't cross those asymptotes. Okay, so remember we went over 1 and down 5. That means I can go over 5, 1, 2, 3, 4, 5, and down 1 and connect the points so that we've got this. And that is our function, transformed. Okay, last thing we got to talk about are piecewise functions. And basically, it's just combining everything that we've just talked about, but onto one graph. Piecewise function, lots of pieces of different graphs. Okay, the key to it, what you want to do when you're graphing these things is you need to know what each endpoint does. Okay, know each endpoint. Okay, for example, you plug in 0 in here. I have the point 0, -5. Can it be equal to that point? Yes, it can. So I'm going to go plot the point 0, -5, 5, 1, 2, 3, 4, and I'm going to put a circle there. Okay? Then to try to simplify things, I'm going to change colors on you so that this one I've got to look at x being 0 and I've got to look at x being 2. So if I put 0 in here, I get 0. If I put 2 in here, I get 8. So that's the beginning and ending of this part of my graph. So can it be equal to 0? No, so I put a hole at that point. 2, 8, can it be equal to that? Yes, so 2, 8 is right here. And that's solid dot. And then the last one is I got to put 2 in. And if I put 2 into that function, I get 1 out. So I'm going to graph the point 2, 1, but it's a hole because it's not equal to it. Now you got to figure out what is each piece doing. Okay, I need less than 0. That means I need this part of the graph. This says x minus 5. Okay, that is, I hope y'all know, is a line with the y-intercept of -5 where we are and a slope of 1. So, and I need to go from here. So if it's going +1, it would be doing this, but I have to go to the left. So I'm going to go down 1 to the right, down 1. I'm sorry, I said down 1 to the right. I meant to the left. Okay? And I have my function. Do I dare freehand it? That's that part. It does go on forever and ever. Okay? What does x cubed look like? Okay? It's the normal x cubed. It starts at 0, 0, over 1, up 1, over 2, up 8. So do your best to make it look like that cubic function. Kind of curves up to that point. That's what that's supposed to be doing. And then my last one is my reciprocal function that we just talked about. And that's the one that's doing this. Goes like that. So from here, I'm going to make it approach asymptotically. And there I have the 3 pieces of my graph. All right, let's look at the last one. We have, again, you want to know each endpoint. So if I put in -5, I get 1. 1 squared is 1. So at -5, I have 1. I got to put -5. Oh, look at this. This is hopefully y'all can see that, our constant function, which means that if I have -5, y is 7. And if I have 2, y is 7. And then this is my absolute value function that's doing this, right? That's my v. But if I plug in 2 into this equation, 4 minus 2 is 2. The absolute value of 2 is 2. So let's go plot each of these. Is it equal to this one? No, we're going to have a hole at -5, 1. I got a hole. Okay. Then I have the point negative 5, 7, which is filled in, and 2, 7. So negative 5, 7, and 2, 7 are filled in. And then I go 2, 2, and that one's a whole because it's not equal to. So over 2 up 2 is a whole. And now we have to talk about each piece. I'm going to do this first piece in the middle because that's easy. It's a constant function. It doesn't change. It's the same thing all the way across. All right. What is that function? Well, I hope you can see that is our quadratic function that normally, that wasn't good, comes down to the 0, 0 normally. Okay. But it's been shifted. Okay. This is inside. Okay. So it's been, I didn't spell. It's been shifted to the inside affects the x, so we do the opposite. So it's been shifted left 6 units. So this 0, 0 point is over to the left 6 units. So that puts it right here. And then we know from our graph it's up 1 over 1 in both directions. And so that should be enough for me to go try to draw a parabola. Okay, there's supposed to be my parabola. And then my function. Now this is a little bit tricky, but if it's in absolute value, hopefully you understand that 4 minus x and x minus 4 are the same thing. So this 4 is inside, so it's affecting my x. Both of these, they were affecting the x and it was a plus or a minus. So I'm shifting it left and right. We do the opposite with the x. So this time I'm going to shift it to the right 4 units. That means this vertex point is going to the right 4 units. So I'm going to go 1, 2, 3, 4. And then I know that my slope is 1. So I'm going to connect it. That's really bad. Probably ought to use my, come down here, use this. So you'll get the idea. And it goes on forever and ever that way. And those are our piecewise functions. So if you want more examples or need to have some questions, please come see me.